Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud, and in this video we will be talking about thermal response tests, or TRTs, and how the data from this test can be used in GHEtool Cloud to further optimize your design or to get the most accurate results. Now let us first start by discussing what a thermal response test is. So I call this the standard way of doing a thermal response test. It's basically just the measurement of the in and outlet temperature of a borehole under a constant injection power. So what we do is we basically drill a borehole with a ground heat exchanger, a grout, etc., like we would for the rest of your project. So it's basically a sample for your entire borefield. Then you let this rest for a couple of days so that your borehole stays in or comes again in thermal equilibrium with the environment. So after a week, for example, you come back with your thermal response rig, which you connect to the borehole, and you let the fluid circulate. And what you do is you measure the temperature. And once you've done that, you're going to start the electric heater in it, and you're going to inject a constant power in the ground. And you keep measuring this in and outlet temperature for 48 to 72 hours. And the reason why this test takes so long is that you have transient effects. So if you recall our discussion on the borehole effective thermal resistance and the short-term effects, we said that this was a steady state behavior, that we have transient effects, namely the thermal inertia of the fluid in the ground. So if you can imagine, if you put hot water into this borefield, this heat is not directly transmitted in the ground. It's first heating up the fluids, and afterwards it's heating up the grout, and then the heat goes to the ground. And we need this longer test in order for the thermal inertia of the fluid and the grout to be done. And if we do such a long test, we can actually calculate a couple of things which are really important for our geothermal design. Namely, we can calculate the initial undisturbed ground temperature, which is, if you recall, really important because it sets the baseline for both your heating and cooling temperatures. So it's really important to measure this. It measures your ground thermal conductivity. So how good the ground conducts heat at your specific location, which depending on the data available can vary significantly. And you can also measure the borehole effective thermal resistance with this method, which is also a really important parameter in geothermal design because it determines how good your borehole can exchange heat with the underground. Now there is a star next to that because you need to be aware that it can happen that the way you design your borefield, for example with antifreeze and a certain mass flow rate, is not the same as the regime or the flow conditions at which the measurements take place. Because these thermal response rigs, they have their own pump, so they have their own pressure drop and pump characteristics and flow rate, etc. And also, typically these type of tests are not done with antifreeze. So you need to be aware that this measurement, at least, the borehole thermal resistance, it should perhaps be corrected when you use it in your design, or perhaps even be ignored. And we will go over that when we hop into GHEtool later this video. Let us now take a closer look on how the temperature measurements can be used to calculate the borehole effective thermal resistance and our ground parameters. So what's shown here on the slide is actually an example of a TRT measurement of 60 hours in this case, and we plotted the fluid temperature. So what you can see is we have a supply and a return temperature, inlet and outlet, and an average fluid temperature, which behaves more or less logarithmically. So initially the temperature increases rather quickly due to our heat injection from the electric heater, and after time this increase decreases in speed, and we end up with this temperature profile which is more or less also what we saw when we were looking at the G function. So if you have not watched that video, it's linked in the description below. Now, what we can do is, instead of plotting it in this logarithmic way, is that we change the axis from a linear timescale with every step 15 hours to a logarithmic timescale. So what we did here is, instead of having the same steps, is that we say, well, at every step we have a logarithmic, so it's 10 times bigger than the last. And our green line here, which was logarithmic, now starts off constantly and then increases and goes linearly further away. And the main advantage of this curve, although it's somewhat more difficult to read, is that we can say, well, after a certain amount of hours, typically after 10 to 12 hours, we end up in the region below, and we can see that our temperature here is exactly linear. So what we can do is we can make a linear regression, which is actually the line you see here, which says logarithmic approximation. And this line, which is a linear curve on this graph, can be used to estimate the parameters. So what we have here is actually the equation that is typically used. Now, if you want more explanation on the equation and the mathematics, please check out the article. This is just to show you quickly how this interpretation can be done. So what we do is we have this logarithmic approximation here. We take the angle, which is here in red. This gives us the k factor in the equation, and the distance between, or at least the height at which the linear line crosses the y-axis, gives us this term m. And both this k and m factor can be used by some couple of more complicated equations to derive the ground thermal conductivity and the borehole effective thermal resistance. Now, we now talked about what's the typical TRT test that's being done. There are also other configurations. For example, you have TRT tests with a constant inlet temperature and a constant flow rate, and where the power actually varies. You have TRT tests with constant inlet and outlet temperature. So here both power and flow rate are varying. You have TRT tests where it's not only extraction but also injection of heat that's being tested. So there are quite a lot of these different tests with both advantages, disadvantages. Some of them are already used in industry, some are more research related, but all of them basically gives you the same output parameters: the temperature, undisturbed ground temperature, the conductivity, and the borehole effective thermal resistance. So with this background in mind, let's look at an example in GHEtool Cloud. So imagine we did a TRT measurement for a specific project. We got an undisturbed ground temperature of 11.78 degrees Celsius. We have a conductivity of 2.32, and we have an effective borehole thermal resistance of close to 0.1 meters Kelvin per watt. So let's jump into GHEtool Cloud and show you exactly where you can enter these values and what difference does it make. So here we are in GHEtool Cloud. I created a new project. Let us now go ahead and fill in all the information from the TRT test. So in our ground tab, we found that the thermal conductivity of this ground was 2.32, and a TRT test always measures the homogeneous ground, so on average for the whole borehole. The ground temperature, it was also measured, and in this case it was 11.78. So this is also again for the average for the entire borefield or borehole. Your borefield In this case, we did a design with 4 boreholes of 100 meter. A borehole resistance, we measured this, so it was 1.03, and our thermal demand in this case is we will have 1000 kilowatt hours per year of sanitary hot water, 15 kilowatts in heating, 8 in cooling, and 24 megawatt hours per year in heating, and 7.6 megawatt hours per year in cooling demand. So we'll send this to the server, and you can see that we stay beautifully between the temperature limits, way above our 2 degrees minimum temperature that we set. So basically, this TRT test showed that this bore field was correctly designed. But now, what we said is, well, we have measured this borehole thermal resistance, but in reality, we will have antifreeze in our system. So let's go ahead and duplicate the scenario and basically say, well, we're not going to measure it, we're going to calculate it instead with a double U-tube, 25% of glycol, let's say, and a flow rate of 0.3 liters per second. And if we now recalculate this situation, you can actually see that your temperature now goes a little bit under the threshold. So there is more than a degree difference between both simulations. And this stresses the importance of calculating your effective borehole thermal resistance. Because if your measurement is not under the same conditions as your bore field will be constructed in practice, you can have quite a lot of difference between your simulation and your reality. So that's always important with your TRT test. Check with the people or the engineering firm who did this. That's what exactly the conditions were of this test, and if the data can be used for your simulation. But otherwise, it's just entering the ground temperature like this, and you will end up with a simulation with the data for this particular project. So this was it for the video. I hope you enjoyed, you learned something new. If it's the case, please consider subscribing, sharing it with your colleagues, and I'm looking forward to seeing you in the next video. Take care. Bye.